In this video, we're going to have a look at the octet rule of a periodic table, or the rule of eights. The periodic table got its name from the way that Mendeleev and other scientists noticed how the properties of the elements repeated themselves periodically. A nice analogy of this is the piano. While the frequency of the individual notes are different, all C's, for example, have a similar pitch. Further to this, you'll notice that in music, the notes also repeat themselves in eighths. In musical terms, we call them octaves. One of the properties that repeats itself is the way that the energy of the electrons increases the further away they get from the nucleus. So imagine a mom, and she's out at the shops with her 3 children. Who is going to have the most potential to get up to mischief? The child that she's holding, the child whose hand she's holding, or the child who's walking ahead? It's going to be the child that's further away, right? The same thing happens with electrons. So the further away they are from the attractive positive center of the nucleus, the more potential energy they have. Now imagine a hotel with different floors. Each floor represents a different energy level, and for our purposes there are 2 different kinds of rooms in the hotel. So there are single rooms which have 1 bunk bed, and there are dorm rooms which have got 3 bunk beds. So obviously a bunk bed can accommodate 2 people, so that means that a single room could hold a maximum of 2 people, and a dorm room could hold a maximum of 6 people. On the first floor of our hotel there is only 1 single room, but the second and third floors have got a single and a dorm room. It starts getting a bit more complicated from the 4th floor up, but we don't have to worry about that for now. Now imagine a tour group of 9 people come and book in at our hotel. So now the rooms get more expensive the higher up you go, so they decide to start booking in from the bottom, from the ground floor. So 2 of our 9 people go into the ground floor over there, so that's 2 of them taken care of. The next person goes into the first single room, and they go into that first bed, so that's that next person taken care of. The 4th person now wants to occupy a room, but the rule is that all rooms have to be completely occupied before they start letting the next room. So our next person goes into the same single room as the 3rd person. So now we've got 4 people in. Now we can start occupying the dorm room. So the 5th person comes in and they've got their pick of beds, right? So they're going to come along and they're going to lie on that bed over there. The 6th person now comes into the dorm room and thinks, why must I share a bunk bed if I've got my pick of the other 2? So he goes to the next bed, and the same with the 7th. So they each occupy a single bed before they start doubling up. But now when the 8th and 9th people, so there we go, 6, 7, 8, when the 8th and 9th people come in, they've got no choice but to double up on the bunk beds that have already been occupied. In our analogy, the different floors are the different energy levels. The different types of rooms are the different types of orbitals, and you get orbitals called S orbitals, like S for single room, and P orbitals, P which looks like an upside down D, the best I could do, P orbitals, and the people are going to be the different electrons. So just to finish this up, we saw that our 9 people were accommodated in total, 2 of them on the first floor, 2 of them on the second floor in the single room, and 5 of them on the second floor in the dorm room. Now the rules for electrons filling up the orbitals in each energy level are as follows. We get the Aufbau Rule, and that is that you have to fully occupy the lowest energy level first. That's why we started at the bottom when we started filling up, and that's why we started with the S orbitals. Pauli's Exclusion principle says that each orbital can have a maximum of 2 electrons provided they spin in opposite directions. That's why I drew the people on my bed facing the opposite way. And the Hund's rule says that no electron pairing can occur in p orbitals until all the orbitals contain at least 1 electron. So that's why we went 1, 1, 1, and then back to the first bed again. To help you visualize Hund's rule, when I set a table, I can never remember which way around to put the knife and fork. So I first do 1 full set. I then do fork, fork, way the forks are all one away from each other and the knives are all one away from each other. In our analogy, this would be the s orbital and those three would be the p orbitals. So instead of drawing stick figures, let's use arrows to denote our different electrons, and we can change the direction of the arrow based on which spin each electron has. So our 9 electrons for our 9 people that came to our hotel would occupy the following energy levels. I've drawn them out here. We would have had 2 on the first floor, so in the first energy level. We had 2 in the second floor in the s orbital, and then we had 5 in the dorm room. But watch how I'm going to fill them up. We went 1, 2, 3, each in their own orbital, and then we went back to double up. 4, 5. And there our total is 2 plus 2 plus 5 gets us the 9. Now how does this relate back to the periodic table? Remember that the periodic table is arranged in order of increasing atomic number, which gives us the number of protons or electrons. So hydrogen would have 1 electron, helium would have 2 electrons, lithium 3, and so on. The s orbitals can hold 2 electrons, and that's why this is called the s block, because they hold, between those two, they hold an additional 2 electrons. The p orbitals can hold a total of 6 electrons, 3 orbitals each holding 2, 3 times 2 is 6, and that's why this is called the p block. And if you count them, we get 1, 2, 3, 4, 5, 6. Now the first row or period of the table relates back to the first energy level. That's why I've done these in the same color. So the first row or period relates back to that first energy level. The second row relates back to the second energy level. In the first row, please don't worry about the fact that the hydrogen and helium are split. They're just the weirdos of the periodic table. For now, all you need to know is that there's only 1 s orbital. As I said, the second energy level has got 1 s orbital and then the 3 p orbitals, which gets us to there. Third energy level, and so on. But from the fourth energy level, it does start getting a little bit more complicated because those transition metals are in between. But we don't need to worry about that for now. So this means that in the second and third energy levels, the total number of electrons that can exist in each energy level is 2 plus 6, which is equal to 8. Hence, Octet Rule. Now when doing a Bohr diagram to represent an atom, it is acceptable to simply space the electrons evenly around each energy level. That's absolutely fine. However, it is possible to combine the Aufbau Principle and Bohr diagrams. So fluorine, with its 9 protons, 10 neutrons and 9 electrons, would then look like this. So there I've put the 9 protons and the 9 neutrons in the middle, and we can put those 9 electrons around the outside. So we had 2 in the first energy level, so I'm going to put those together because they're in the s block. Then I start in the second energy level and I've got 2 in the s block again, and then I start filling up that p block. So now I go 1, 2, 3, 4. Now I go 5, 6, 7, 8, 9 in total. So that would be a more Aufbau looking Bohr diagram, but you will see examples of both. Ones where the electrons have been completely evenly distributed around, and ones where they've actually been placed more into their orbitals. It's important to know that the electrons don't actually sit next to each other within their orbitals. The different orbitals have got different shapes, and that's something that you're going to learn about at a later stage. But it's just a way for us to denote the different energies that the electrons have and where they are most likely to be. Now, the number of electrons in the outermost energy level of any particular element is called the valence electrons, and the electrons which are in the filled energy levels before that are called core electrons. So in our example for fluorine, fluorine is going to have 2 core electrons because the only filled energy level is the first energy level where there are 2 electrons. So those are going to be our core electrons. And it's going to have 7 valence electrons because in the second energy level, we've got 1, 2, 3, 4, 5, 6, 7 in total, and there's the 7 in the second energy level. Now this corresponds to the fact that fluorine, over there, F, fluorine is in group 7 of the periodic table. How cool is that? So we've covered a lot in this video, and I hope that this has improved your appreciation for how awesome the periodic table is in the way it so cleverly represents all the trends of the elements. There's still a lot to learn, but I hope that this is a good start.